Hi, good morning, everybody. Welcome. So it's day 4. I don't think anyone is tired. I think everyone is warmed up, right? And now we're ready for for what comes next. So this morning we're going to be talking about Monte Carlo methods. So first order of business. My name is Charles Margoissan. I'm a research fellow at the Flatiron Institute in New York City. This is a fairly new institute that's dedicated to applying computational methods to the natural sciences. So things like physics, astronomy, neuroscience, and I just wanted to put a picture of, this is the terrace of the institute where we have lunch. We're right in downtown New York, as you can see. So if ever anybody is in New York City, you should feel free to stop by. And we do hire postdocs. I think this is one of the best places to work at. I've certainly tremendously enjoyed it. I myself am in the computational mathematics department, and I'm a statistician by training. Some of you know what that means. We're fortunate to have 2 teaching assistants today. One of them is Austin Garrett, who is a software engineer from Arizona, and then we have Bob Pepin, who is our local expert. They'll be going around and helping you with the exercises. And then what I'll say is, you should feel free to ask questions at any point. If you need some clarifications, if you have a comment, any question that's 1 sentence long is fair game. All right, so this is a rough outline of what we're going to do. We're going to talk about Monte Carlo methods, and there are a lot of ways to do Monte Carlo methods. In fact, in the previous days, you've already used some Monte Carlo methods, so we'll allude to that. And we're going to spend a fair bit of time on something called Markov chain Monte Carlo. We'll do 2 applications, one warm-up application, which is a Bayesian linear regression. You've encountered some form of that. And then we're going to focus on a disease transmission model, which is an example from epidemiology. This is the kind of thing that was used to model COVID-19 outbreaks. And the reason why I want to do that is I think that to really, really use these computational methods in a principled way, you need to really understand the problem that you're applying them to. So we're going to ground this discussion in a problem that hopefully everyone can reason about fairly well. We're also going to talk about importance sampling, and we'll use that to do things like model comparisons, cross-validation, these sorts of tools that you would apply in a general setting. And at the end, we'll have a discussion. And one of the items I'll discuss is, for example, when should I use a sampling method like Markov chain Monte Carlo, and when should I maybe use something like variational inference? And we'll have a bit of an open discussion on that. Okay, one disclaimer, and I got this from interacting with the TAs. So I just want to say that we're not going to be building Monte Carlo methods from scratch. This is more of an applied lecture. We're going to learn how to apply Monte Carlo methods, and we'll use very powerful implementations that exist out there. But my experience interacting with scientists is that unless you understand how these methods are implemented and what's going on under the hood, you're not going to be applying these methods well. So we need to discuss some of the theory, we need to discuss some of the implementation, and we'll do that in a pragmatic way. Okay, the other thing, just regarding the languages, so we're going to be using R scripts and the probabilistic programming language Stan. So my understanding is that you've had some exposure to Stan on Monday in Andrew Johnson's course on Bayesian workflow. I'm not going to assume you remember anything from it, so we'll go a little bit over it. But I want to emphasize that even though I'm using R as a scripting language, all the algorithms we're going to run are going to be in Stan, so that's with an underlying C++ library. And this is not a course on R, right? It's just a convenient scripting language. You could also interface Stan with Python, or maybe some of you use Julia, and I think even Rust is an option. Or if you hate languages, you can do it in the command line. There is a notebook with the exercises, so it should be on the usual GitHub from the Probabilistic Summer AI course. I've also put a link to my own GitHub. So if people have their computers, we're just going to open that notebook because there's some installation that needs to happen. So I'd rather, we do the installation ahead of time. I think it doesn't take more than 5-10 minutes, but just in case, we'll do it. That way, when we get to the exercises, and we're going to do a bunch of exercises, right, we'll be ready to do that. Okay, so, right, great, right? So it's kind of, I hope you've gotten used to this. I find a notebook, I open it in Colab. There's a dark mode for Colab, by the way. Right, and what I'm going to do is, so we can look at the runtime. By the way, Colab does give you a bunch of runtime options. So you can run things on CPUs, GPUs, and TPUs. Let's stick to CPUs for this. And one of the reasons is because we're going to be solving differential equations. Works a little bit better on CPUs, and we're not going to really need the parallelization capacities of a GPU. But I think by default, Colab starts on a CPU. And then all I'm going to do is, okay, so this was not authored by Google, so you should be really wary about whether you can trust this Colab. So we're going to run it anyway, at our own risks, but I promise you there's nothing malicious in this code. All right. Is this better? All right, cool. Right, and so now we're going to run these 2 lines of code, install packages and if install packages, and what that will do is it will install R, right? And now that's running in the background, and we're not going to worry about this for a while. Okay? If you have any questions, our 2 TAs, Austin and Bob, are at the front, right? So just raise your hand, and you can solicit their attention. With that out of the way, let's get started with, aim and scope of Monte Carlo methods. So our motivating problem is going to be very simple and very general. We're going to try and compute expectation values with respect to some target distribution pi, okay? So here are a few areas where this problem might arise. So originally, this comes from statistical physics, right, where people have some unnormalized distribution that's defined by an energy, right? They're trying to compute expectation values, entropy, those sorts of quantities, right? The prototypical example would be the Ising model. Another example is Bayesian inference, right? Here, our target distribution is going to be our posterior distribution. And a third example would be in variational inference, where this Q is our approximating distribution, and we want to compute an expectation value with respect to Q, for example, to get a stochastic estimator of the elbow, right? And so, one question that I want to ask, especially about the posterior distribution, is what are we trying to learn about the posterior, right? I think people, the phrase, we're approximating the posterior, we're computing the posterior, right? What does that actually mean, to approximate the posterior, to compute? What are we trying to get out of that? People who have been here for 3 days and computing and approximating posteriors, what do you think?
Samples that are distributed to the distribution close enough to the one that we have.
Okay, so one answer is, well, really, we're trying to get samples, right, from that distribution. Yeah, that's true in some applications. Right? I think that when you're trying to imitate, a data generating process, something that generates images, right? Your goal is to generate images, right? Your goal is to do samples. Okay, but what about if I'm trying to, I'm interested in a posterior distribution, as opposed to, say, a marginal distribution? Is that my end goal? Could be, but what else do people think?
The uncertainty and the expected value.
One more time?
The uncertainty and the expected value.
The uncertainty and the expected value. I like that a lot, right? So maybe if I can rephrase this a little bit, what you're saying is, I want to compute summaries of the posterior distribution, and usually one summary will try to characterize, a central tendency. So I could use an expectation value. I could use a median also. And then I also want to characterize uncertainty. So how might I characterize uncertainty? I can estimate a posterior variance. I can also estimate a posterior interval based on quantiles, right? But the point is that the way we actually deal with these high dimensional distributions is we work with intelligible summaries, right? And so these summaries are going to be things like expectation values, variance, quantiles, right, of some distribution f of interest, right, where f is some transformation of theta, right? And all these quantities are with respect to pi. That's really what we're trying to do, right? And what Monte Carlo methods do is they say, well, look, if you're able to generate samples from a target distribution, right? So first of all, you might solve your simulation problem. That's a valid task to solve. The other thing is, if I want to estimate a mean, I just average my samples. If I want to estimate a quantile, I just take a sample quantile, right? Once I have access to samples, I can construct estimators, or in this case, Monte Carlo estimators. And this is what I'm going to care about. Constructing accurate Monte Carlo estimators that give me useful summaries of my posterior distribution. Now, we've seen in variational inference that, you have access to exact samples, right, of your approximating distribution, or maybe if you're using the reparametrization trick, you just draw samples from a standard normal, right? But in most problems that we're interested in, we don't have access to exact samples. And so we're going to have to come up with a way to generate approximate samples from our target distribution, such as a posterior. Okay, so that's going to bring us into Markov chain Monte Carlo. Any questions about this?
In your experience, how are these posteriors actually used in practice? Like, what do people do?
Yeah, excellent. And that's why, we're going to look at a very specific example from epidemiology, where we'll really dive into what people do with, samples from the posterior.
They make a lockdown on that in your posterior.
One more time.
Using the posterior, they, for example, make a lockdown in your New York City.
A lockdown. So, but that's an example, right? So let's say you want to make a decision, right? And you have a disease that you don't understand that well. You have a lot of uncertainty, right? What is the optimal decision you make under uncertainty, right? So that's an example, right? You try to estimate the mortality rate, the number of deaths if you implement this policy or if you don't implement this policy. There are quantities that went around, like R0, right? Which is how many people will one infected individual infect, right? And this is kind of used to understand the dynamic of the disease, right? So that's one example. The other thing is you make predictions, right? You're trying to predict a trend. You're trying to predict an outcome. But maybe in your prediction, you'll want some uncertainty quantification, because I don't just want to know what is the expected number of deaths. I also want to have some handle of, what is one of the bad case scenarios. And maybe I want to be a little bit conservative with something like that, right? I can give more examples, and we'll get into more such examples. But thanks for the question. Yes? So I think your question is, can we do Monte Carlo even if we don't have samples from the distribution? Yeah, that's what we're going to do. And I'll explain how. And then you can tell me whether you think it's possible or not. Okay, so let's keep going. So again, here I'm going to focus. I'm trying to estimate an expectation value, right? If I have Monte Carlo estimators, here I would just do a sample average, right? and I can do, sample estimators of a bunch of quantities. All right, so first question, how good is such an estimator? Right, so here I'm assuming that I have exact draws from my target distribution, and I'm going to say I want to control the expected squared error of my estimator. Right, so typically I'm interested in the squared error. Now, a sample average is a random quantity, so I'll take an expectation value. And that error decomposes into a squared bias and a variance, right? So if I have IID, so that means independent and identically distributed samples from my target distribution, it's going to be unbiased, and then the variance of the Monte Carlo estimator is going to be equal to the variance of f of theta divided by n. All right, I have a question for you, and this came up yesterday, right? How well does this scale with dimension?
Doesn't seem to depend.
Okay, so I first heard a response on the second one. It says, it doesn't seem to depend on dimension, right? What did you say back there? Yeah, okay, we'll get to the central limit theorem in a second, but we don't, next slide, so you're ahead, so that's good. But yeah, I mean, there's no explicit dependence on dimension here, right? The only place where dimension can come in is if the variance of f itself depends on dimension. And so there are going to be some cases where it does, and a lot of cases where it doesn't. So if I'm trying to estimate first and second moments in quantiles, oftentimes it doesn't depend on dimension. Now you can construct some examples where, for example, you're trying to estimate an expectation value of a log density, and then that log density, grows in scale as you increase the dimension, and now you can pick up a number, you can pick up a dependence on dimension. But there's nothing intrinsically in Monte Carlo estimators that makes it depend on dimension. I just want to clarify that point. And that's why it's used so much to compute integrals, right? So if you had a scheme like quadrature, for example, here you would really pick up a dependence on dimension and a curse of dimensionality that makes it impossible to apply these methods beyond, 5 or 10 dimensions. Monte Carlo method, you can actually apply to much higher dimensions.
Usually, I mean, my statistics is not that strong, so I just remember one lecture from my master's, they mentioned that if we don't know the variance of the population, and these are probably the samples, so there is this 1 by n minus 1 for the loss of degree of freedom that we are getting for the variance from the samples. So is this also related to the Monte Carlo samples that we take?
No, not quite. So you're thinking about the sample variance, and I'm happy to discuss that point offline. We'll clarify that a little bit. Yeah. All right, who said central limit theorem? There it is. So in addition to characterizing the expected squared error, I can also tell you that the Monte Carlo estimator, right, if I have enough samples, is actually going to be roughly normally distributed around the true expectation value, and this is its standard deviation. And this is a very, very powerful result. It's a very general result. It's saying, look, under some mild conditions, whatever you draw your samples from, averages at some point start behaving like normally distributed quantities. And that really allows us to characterize well the error of these Monte Carlo estimator. And I hope you appreciate the power of this central limit theorem. It's one of the crown jewels of probability theory. All right, so now let's get to the interesting point. We want to generate samples from a posterior distribution. We can draw IID samples. We're going to use something called Markov chain Monte Carlo. So let me first explain the procedure, right? And then I'll claim that it works. We're not going to do the exact proofs, but we'll develop some intuition as to why it works. And the idea is, well, instead of starting from my target distribution, which I cannot draw a sample from, I'm going to start from some initial distribution P0 that I'm able to sample from. Could be a prior distribution, could be a fast approximation of my posterior, maybe via variation and inference, for example. And then I'm going to do what's called a transition kernel, where based on my current sample, theta I, I'm going to generate a new sample, theta I plus 1. Here's the claim. If you construct the transition kernel carefully, you can actually, by applying the transition kernel over and over and over and over and over and over and over, however big that infinity number is, over and over again, you'll get a sample from the true posterior distribution. So really what we'll construct is a stochastic process whose stationary distribution is our target distribution, P of theta given I, Y. Right? So eventually, if you throw enough computation, you get the result that you want. Now in practice, we have to work with a large enough n, and what we'll see is that even if you don't go to infinity, you're still able to get samples that are approximately from your target distribution. Even though, and I want to emphasize this, they're not from your target distribution. They're merely approximately from your target distribution, and we're going to characterize exactly what that means. And we're also going to worry about what does large enough mean, right? How long, how many times do I have to apply this transition kernel to get something useful? Right? The other things that I'll emphasize is that the first samples for a low n suffer from a large bias. Who can tell me why that is? For a chance to go to the canal tour. No, I don't have that power. Yes?
Because in the beginning you actually don't know where the mass of our probability is. So if you sample something randomly, we likely come up with a region which, even if we draw like 1,000, 10,000 samples in the end, is still all presented by one sample in the beginning.
Okay. Let me try and paraphrase what you said, because I think that answer is correct, right? But basically what you're saying is at the beginning, this P0 is what are the odds that it actually, you know, describe our target distribution well, right? And probably not, right? And so if I draw samples from P0, right, or from distributions that are close to P0, then my Monte Carlo estimator is going to suffer from a bias, right? Is that the idea? Yeah. And so what we're going to do is we're going to have what's called a burning period where we're going to discard the initial phases, right? We also call it a warm-up phase, right? And warmed up is what we all are, right? Nobody is tired, everyone is. Okay, so here's an example of how we might construct such a transition kernel. By the way, this technology is old, 1953, right? The Metropolis paper. Metropolis, Rosenblatt, Teller, and Teller. Right? 2 married couples worked on that paper. So we start with an initial distribution from P0, and then this is our transition kernel. Here's how it looks. We're going to propose a new sample, and it's going to be a perturbation of our existing sample. So there are many ways to do perturbation, and there's still ongoing research about what is the best way to perturb our initial sample. Most straightforward way to do it is a Gaussian perturbation. Right? And then this is going to be our proposal, and we're going to accept the proposal with some probability, right? In particular, if the proposal has a posterior density that is larger than our current sample, we accept it with probability 1. If the proposal has a posterior density that is lower than our current position, we might accept it, we might reject it with some probability less than 1. A quick question. In practice, can I compute this ratio of 2 posterior densities? Alors, okay. I was trying to see if someone else, but yes, go ahead.
Yes, we can, because it's a ratio, so it's a ratio between the, like a marginal distribution. You can compute the conditional distribution, but you can't compute joint distribution.
Okay. Yes, I think this is mostly correct, right? Which is that we can compute the, so okay, the posterior, we usually can't compute it because there's an unknown normalizing constant, right? If I take the ratios, the normalizing constants cancel out, right? So really the ratio of the posterior distribution is just the ratio of the joint distributions. Or if you want the ratios of the likelihood times the prior, right? So that's a quantity that I can compute, even if I don't know the normalizing constant. And so once we do this, right, we're going to have what's called a Markov chain. Right? We're going to construct a chain, and those are going to be our samples. So this is what it looks like in action. So here on the left-hand side, I'm starting 5 chains at different locations, and then I start running them, right? Where I'm applying that transition kernel, I do a perturbation, I accept it with some probability. And eventually, the Markov chains are all going to start drifting towards the center, which is where the probability mass concentrates, right? Regardless of where they started, they're all drawn to the same region where the probability mass concentrates. And then at the end, I'm going to discard those initial samples that are biased because they start far off in the tails, right, because of my initial distribution. And I'm going to be left with some samples that approximately come from my target distribution. And this is what I'll use for my Monte Carlo estimators. So what are the benefits of the Metropolis algorithm? Well, one, it's extremely simple to implement, and it has those nice asymptotic guarantees that eventually you will get the right result. But there are some drawbacks. So, you know, asymptotically can be a very long time. In the finite regime, the samples will be biased, right? So we somehow need to deal with that. And then the other thing is that the samples are not independent, right? They're correlated to one another, right? I'm always doing some perturbation. And we'll see that that autocorrelation of the Markov chain is going to increase the variance of our Monte Carlo estimators, right? So remember my goal, I want to control the squared error of my Monte Carlo estimator. I need to worry about the bias and the variance. All right, here's another example. So, you know, for those who enjoyed the lecture on SDEs yesterday, this is actually an example of an SDE where we're going to take an MCMC algorithm, so a Markov chain, which is a discrete process. We're going to approximate it as a continuous process. So it's actually a Langevin diffusion. And the idea is I have some initial distribution, P0, that starts from a Gaussian, some target distribution P, that's a Gaussian with a different mean and a standard deviation. I can work out, you know, by applying this Langevin diffusion process that after some time T of running the process, I'm going to have a sample that's distributed according to some normal distribution that somehow lies between the initial distribution and the target distribution, right? So who can tell me the distribution of theta t at t equals 0? Yeah, P0. I heard a chorus of murmurs of P0 as P0 has entered the room. What if t goes to infinity? P, correct. Right, so you extrapolate, and then in between, you know, even if t doesn't go to infinity, you can convince yourselves that if I look at the expectation of value of theta t, right, it's gonna have a bias relative to my target distribution that decays exponentially. And similarly, the standard deviation is going to move exponentially from the initial variance, which is sigma naught squared, to the target variance, which is sigma squared, right? So we're evolving very quickly from one distribution to the other in this example, right? And the thing that I want to emphasize is that because you have this exponential decrease in the bias, in this example, for t large enough, the bias becomes negligible, right? And so that's why people tend to say, look, Markov chains Monte Carlo, they give you unbiased estimates, right? It's not quite correct, but for all intents and purposes, it's correct enough.
Is this similar to the diffusion process that we learned yesterday?
Yeah, so the question is this similar to the diffusion process that we learned yesterday? And the answer is yes. Yes, it turns out that this diffusion process, so I didn't know yesterday that you could use it to describe ladder VAEs. That was really fascinating to me. You can also use it to describe Markov chains processes. Yeah, it's a continuous version of a discrete process. Okay, let's talk about the variance of the Monte Carlo estimator, right? And I'm gonna make an assumption. I'm gonna say, suppose that the chain is stationary. So what that means is I've run it for long enough that now it's approximately drawing from the posterior distribution, right? I have a central limit theorem that tells me that my Monte Carlo estimator, and remember now I'm no longer using exact draws from the target distribution, nonetheless, under some regularity conditions, I can still get a central limit theorem that tells me that this Monte Carlo estimator is going to be approximately normally distributed, right? And now the variance, instead of decreasing with n, the number of samples, is going to decrease with a quantity called the effective sample size. And the effective sample size looks like this. It's going to be n with some penalty term due to the chain's autocorrelation, right? So this rho t quantity here is going to be the correlation between two samples that are separated by t transitions. And the reason why that is because, well, you know, if instead of generating independent samples, you're generating samples that are close to one another, you have a loss of information, you know. It's not quite the same, you know, and you can imagine that if it's strongly correlated, then you're really just generating about, you know, one sample, right? Whereas if they're independent, you're getting more information out of it. So just as a sanity check, if I have no autocorrelation, what is my effective sample size? N, correct, right? This rho goes to 0 and then you recover n, and this is what you would expect, right? On the other hand, we're going to suffer from rho t, so somehow we're going to have to worry about the autocorrelation of the Markov chain.
Is there a case in which n, so the effective sample size is higher than n?
There is a case. Does anyone want to guess when that happens?
When the chain is not able to find probability mass, or the autocorrelation is... Can autocorrelation be negative?
Yes, okay, so the answer is when the autocorrelation is negative, right? So technically you can construct Markov chains, Monte Carlo, that generate anti-correlated samples. And so that gives you what's called super efficiency. And super efficiency, it's not a hype word, it's a very precise technical term that means you're doing better than independent samples, right? And so the way in which this could happen is, you know, you can imagine that, you know, if you have a Gaussian distribution, you're kind of like jumping from one side to the other, right? And so then you take any two samples, they always average out exactly to the mean, right? What ends up happening is that whenever I have an anti-correlated Markov chain, I can get very good estimates of, let's say, the first moment, right, so the expectation value, but it gives me bad estimates of the variance, right? So in practice, yes, super efficiency is a thing, and there are cases where all we care about is the expectation value. Again, variational inference, I want to estimate the elbow, right? That's an expectation value of a ratio of log densities. I don't care about the variance of that, right? And so here, anti-correlations or techniques that reduce, you know, so things like control variance try to do that, right, can be viable strategies. Can be viable strategies.
Excuse me, does this also mean that if I have an infinitesimal but constant autocorrelation, still the effective sample size is 0?
If you, sorry, one more time?
So if I have the autocorrelation is constant but very small.
Is this going to blow up? So here, no, because your rho t is going to go down with t. Remember, t is the separation between two samples, so you can have a constant autocorrelation between neighboring samples, but nonetheless, then your rho t decreases linearly with t.
Yeah. I meant if it was constant, even with constant in the delay.
Mm-hmm.
So in that case, it would still be 0. If that is achievable, I'm not sure. So we could have 10 to the minus 10, but still the effective sample size would be 0.
Yeah, let's talk about that. I understand your point. Let's talk about it offline. In practice, it doesn't happen, but let's talk about it offline. I see your point. Yeah. Okay. So now let me go back to handling the error of MCMC. Our strategy here is we're going to have two phases. We're going to have a warm-up phase where we're going to discard the initial steps because we don't want the bias that is due to the fact that we didn't start from our stationary distribution, but some initial distribution. And then we're going to have a sampling phase where we're going to try and generate a lot of samples so that we can have a large effective sample size and reduce the variance of our Monte Carlo estimator, right? All these questions of how expensive should Markov chain Monte Carlo be essentially boil down to this. We're trying to control the bias and the variance. And in my experience, most of the people who use MCMC only have a limited awareness of this. And in fact, I don't think that we use MCMC in an optimal way because in practice, it's not straightforward to know ahead of time how long the warm-up phase should be or how long the sampling phase should be. And we're going to discuss a little bit some strategies to deal with that, right, in today's talk. And then I'll be very candid about what are some outstanding open questions here.
Is it somehow obvious that you should have this deep cut that you either throw away or accept the sample? I mean, it sounds like a rough approximation to some weighting of samples.
Yeah. So the question is it clear that you should have a deep cut? Could you instead do some weighting? You might be able to do some weighting. Some people do it. But in the end, what ends up happening is that the first samples are just weighted to 0. Right? So it's effectively the same thing. Now, maybe there's some more refined things. There are some cases where so the initial samples, they actually not only contribute bias, they also increase your variance. And that's because you have a drift in the chain where you have samples that follow different distributions, right? But eventually, once you get close enough, you kind of get a bias variance trade-off, where some of the samples might contribute bias, but they'll also reduce your variance. And so how does that play out? So there are some people who think about these problems. I can give you some references if you want to dig deeper into that. Okay, so now the question that we need to ask is, that's all great, but how do I construct my Markov chain in the first place? Which transition kernel should I use, right? So I gave you one example. There was the Metropolis algorithm from 1953. Then there was the Langevin diffusion approximation, but that's really an approximation in a very special case. And as you might suspect, since 1953, some progress has been made in the field of Markov chain Monte Carlo. Not to undermine how cool the Metropolis algorithm is. It's really seminal. And so there are a lot of different possibilities. So one of them is this Metropolis adjusted Langevin approximation, where you're actually going to take this stochastic differential equation, do a discrete approximation of it. We're going to look at something called Hamiltonian Monte Carlo, which I suspect Andrew Johnson mentioned on Monday. So what's the motivation? So let's suppose that I want to sample from this distribution, right? So this is a Gaussian with two correlated samples. If I did the Metropolis scheme, which is really a random walk, right? What would happen? So I do a normal perturbation, right? So you can imagine that this circle represents my normal perturbation. Then, if I propose within the ellipse, then I'm going to generate a sample with a high posterior density. I'm going to accept it. But most of the time, I'm going to step outside of the ellipse. And so I'm going to generate a sample that gets rejected. And so what ends up happening in Metropolis is the second there's some interesting geometry in your posterior distribution, you start rejecting the samples a lot of time. Okay, no problem. What we can do instead is we do a smaller perturbation so that we're less likely to step into a region that has a high density, right? So now I have a high acceptance probability, but I'm only taking small steps, which means it's going to take me forever to move, from one side of the ellipse to the other side of the ellipse. Right? That's the intuition in low dimensions. More generally, that means you're going to have very strongly autocorrelated Markov chains. And what is the problem with autocorrelation?
The variance
yeah, autocorrelation increases the variance of my Monte Carlo estimators. So I'm going to need to generate a lot of samples to make the variance go down. There's an alternative algorithm called a Gibbs sampler, where essentially you update one coordinate at a time. You're kind of going to suffer from the same problem, which is that you're only able to take small steps whenever you have some interesting geometric structure in your target distribution. So we're going to use a scheme that's a little bit more sophisticated called Hamiltonian Monte Carlo. And the phrase Hamiltonian comes from Hamiltonian dynamics of classical physics. And the idea is that we're gonna look at our posterior density, and we're going to treat it as a physical potential, right? I'll explain in a second what that means. But you can think of it as, you know, a physical potential. It's you know, for example, when you have an object that's moving across space, and there's a gravitational object that's doing a pull on it, like the Earth, right? It's going to exercise a gravitational potential that's going to inform the motion of that object. In addition, we're going to give the Markov chain a momentum. And so what that means is, instead of taking a random step, which is what that metropolis perturbation does, we're going to give the Markov chain a random shove. And then we're going to simulate the laws of classical mechanics, where we're going to evolve the initial position of the Markov chain and the initial momentum of the Markov chain to a new position and a new momentum. And the way we do this is by solving Hamilton's equations of motions. So for those of you who have done some physics, this will look familiar. But let me kind of provide, you know, the intuition here. So suppose that this is our potential induced by a posterior density, right? So this is a quadratic potential. This is what you would get out of a Gaussian. If my particle is here, and I give it a shove, then what's going to happen is the change in momentum, equivalently the acceleration of the particle, is going to be driven by the gradient of my posterior density, right? And so I'm going to start accelerating towards region where the posterior density increases. Conversely, if I start moving in regions where the posterior density decreases, I'm going to start decelerating. And so if I look again at something like this ill-conditioned Gaussian, you know, I can give it a shove, and maybe if it just kept going straight without paying attention to the gradient, then eventually I would end up in regions of high densities. But as I start moving to the edge of the ellipse, I decelerate, and then eventually I turn around, and then I start falling back, right? So utilizing the gradient gives us a way to move across this parameter space in an efficient way. And in particular, the other thing I could have done is, suppose that I give it a shove that's outside of the ellipse, right? So completely in the wrong direction. What happens? The particle just decelerates very quickly and then turns around. Okay, so there are some challenges. So HMC is a bit more complicated than the metropolis algorithm. So one of them is we now need access to the gradient of the log posterior density. Is this a problem? Is this quantity hard to compute? Someone else. I know you know, someone else. Yes? Exactly, right? So the gradient of the log posterior is the gradient of the log joint, right? Because the normalizing constant doesn't depend on the parameters. So it gets dropped out. And then in practice, you know, there was a dark time where people had to code gradients by hand. And it was very time consuming and error prone. And now we benefit from automatic differentiation. I can't tell you how amazing automatic differentiation is, because we're going to construct some pretty fun posterior densities, and we'll just get the gradients automatically. The other difficulty is there are a lot of tuning parameters when we're constructing this HMC. So one, we need to decide how long are we going to simulate the Hamiltonian trajectory, right? So obviously we want to go far enough, but at some point, we're just going to start going in circles, and we're going to be wasting precious computation time. We need to solve Hamilton's equations of motion. That's a differential equation. So we need to tune an integrator. We need to figure out what the step size needs to be. And then any physical particle needs to have a mass. Who can tell me what the mass of a Markov chain is?
Wow.
It could be, right? I mean, it's whatever you want it to be, right? But actually, 1 is not an optimal solution at all, right? We can come up with better solutions. So there are all these tuning parameters, and I should say that Hamiltonian Monte Carlo, that's also pretty old, right? Original paper, 1987, quantum chromodynamics, right? But it wasn't until 2014, 2012, 2014, that Hamiltonian Monte Carlo became one of the most widely used, if not nowadays, the most used Markov chain Monte Carlo algorithm by the scientific community. And the reason why that is because Matt Hoffman, while he was doing a postdoc at Columbia University with Andrew Gelman, so for anyone who's contemplating doing a postdoc, this is either inspiring or depressing, right? Figured out a way to do a self-tuning Hamiltonian Monte Carlo, and what that means is during the warm-up phase, not only are we moving towards the target distribution, we're actually adaptively learning what an optimal length should be for the Hamiltonian trajectory and what the precision should be when we tune the integrator, right? So he came up with a very viable solution called the no U-turn sampler, or the NUTS algorithm. And I should say, by the way, is that finding good adaptations of Hamiltonian Monte Carlo is still an active area of research. There's very impactful research, like if you can improve the adaptation of Hamiltonian Monte Carlo for certain problems, you can have a big impact on a lot of scientific work. Right, and so the good news is that Stan implements, so the big contributions of the probabilistic programming language Stan when it came out is it had a very rich and efficient automatic differentiation library, which kind of kept growing over the years, and it had this adaptive implementation of Hamiltonian Monte Carlo. Just to give you an example, so here I have this ill-conditioned Gaussian that's very high dimensional. On the right, I have independent draws. On the far left, I have Metropolis. So you can see how even after many iterations, Metropolis is kind of failing to move across the parameter space. So what is that going to do to our Monte Carlo estimator? Yeah, high variance, right? And this is potentially biased. This is probably biased, right? The Gibbs sampler does a little bit better. Again, potentially biased, likely high, I mean, definitely biased. High variance, it's going to take you a lot of time to really get some useful Monte Carlo estimator. And then with the no U-turn sampler, you can't even distinguish it from what you would get from independent draws, right? In this example, look at the paper for high details. There's a paper by Mike Betancourt called A Conceptual Introduction to Hamiltonian Monte Carlo. He also goes over Markov chain Monte Carlo. If someone really wants to go into more details, you know, more accessible details, non-measure theoretical detail, I really, really recommend Mike's paper. It's really fantastic.
Excuse me? Question, probably a naive question. Maybe I'm not getting it. I'm looking at the Metropolis. I'm not seeing that as a high variance. I'm seeing that as underexplored space. Why doesn't it need to high variance?
Okay, great. So the question is, you look at the Metropolis, and it doesn't look like there's a high variance, right? Because all they're concentrated. So why does this mean that our Monte Carlo estimator has a high variance, right? So that's a very nice question. And what I'll say is that if I draw one sample that has no variance and it's super concentrated, but your Monte Carlo estimator is going to have a very large variance because it's based on one sample, right? So it's not that, yes, you're right. If I took the sample variance is small, right? But what I care about is the variance of my estimator. So the idea is that if you were to repeat that procedure multiple times, sometimes you'll get a concentration here, or a concentration over there, and a concentration over there, right? And so every time you would generate Monte Carlo estimators, there are in violent disagreements with one another. And that's where the variance comes from. Yeah. So good question. And we have to think, when we think about variances, we need to think about population distributions. What if we did this procedure multiple times? What would happen? Would we get consistent results, or would we get different results? And here I'm using consistent colloquially. So statistics has this horrible manner of taking words that are perfectly normal and ascribing them technical meaning. So for example, I can't say that a method is powerful, because powerful is used in hypothesis testing. And so makes it difficult to write papers, or easy, depending on how you look at it.
Is it safe to assume that if we initiated multiple chains in Metropolis and each chain is independent of the other, would this still converge? And you mentioned that there is this sample variance, variance. Even if they converge at different places, can we assume that it will still map out the posterior?
Right. So the question is it safe to assume that if we started different Metropolis algorithms, they would all converge to the same space? And so you can expect that they're not going to converge to the same space. And in fact, this is going to be a technique that we're going to use to detect whether the Markov chains have converged. We're going to run multiple chains, and we're going to check whether the samples we get from different chains are in agreement with one another. Now, the problem is that, yeah, maybe by chance, the different Markov chains will. So, okay, I should be very careful here. So here in low dimensions, we can think about covering the space. I just want to make clear that this idea of we're generating samples to cover the space completely breaks down in high dimensions. We don't need to cover the space to get accurate Monte Carlo estimators, right? So let me just say that if you have different chains that have not converged, maybe by chance you get an accurate Monte Carlo estimators, and there are techniques to try and do clever averages of Markov chains that have not converged. Your question was, is this safe? My answer is, it's not safe. Okay, so I think we're moving at a reasonable pace. I don't know that we're going to cover everything, but I'm more interested in having these discussions and answering questions than exhaustively covering everything, just as a disclosure.
Yes, I have a question about these adaptive settings that you adapt in the warm-up period for no U-turn Monte Carlo. So when you say that you have an adaptive mass matrix, what exactly does that mean?
Yeah, okay, good question. So, okay.
Trajectory lengths at this, they're kind of disconnected, so it's
Yeah, so they're absolutely connected, right? So I think that, so the question is, what mass matrix could I possibly learn, right, when I'm doing HMC? And so one way, just to continue the analogy to physics, one way to think about it is that mass is resistance to acceleration. So now I think about what are the directions in which I want to accelerate and the ones in which I don't want to accelerate a lot, right? And so you kind of have a sense here that you want to accelerate a lot along these directions and not that much along these directions. So the way you do that is you match the inverted mass matrix to the sample covariance matrix. And so the strategy that's being used is that we use the early samples from the warm-up to estimate, to do a somewhat crude estimation of the sample covariance matrix, and then we set the inverted mass matrix to that, right? That's one way to do it. You can also think of it as a preconditioner. Maybe some people are familiar with that idea, and I'm happy to talk more offline. But there's interesting research on what is an optimal mass matrix, and it's going to depend on the problem.
So is there some equivalence between this mass matrix and the parameterization of my variables? I mean, in physics, particles are just mass.
Yeah.
Intuition for all diagonal element of mass matrix.
Yes. So the question is there a relationship between reparameterization and mass matrix? The answer is yes. And we can talk more about it offline. Let me move a little bit. I know I said I wanted to have discussions within reasons, right? So let's keep moving. Alors, by the way, do we have a scheduled coffee break? When is that? 10:15. Okay. So here's what we're going to do. We're going to keep going, right? And at 10:15, at 10:30 we'll do a break. Does that sound good? People have the stamina? Okay. If it's earlier, it's earlier. All right. So let's just do a warm-up example. Okay. So Stan is, Stan is a language that is used to specify a joint probability distribution, right? And what we're going to do is we're going to pass in some data and then some tuning parameters for MCMC. In fact, we're going to declare what algorithm we're going to use. And then the output is going to be approximate samples from the posterior distribution, and then we're going to do any number of operations on these samples to construct Monte Carlo estimators and also diagnostics. I should say that there's a lot of different inference that you can do with Stan. So one of them is Hamiltonian Monte Carlo, or NUTS. It also supports variational inference, right? In fact, some of the early black box variational inference came from the Stan project. Okay, so we're going to use R as a scripting language, but you can interface it with any number of languages. There's fantastic documentation, not only on using Stan, but on Bayesian modeling. So I've seen several authors of other probabilistic programming languages, for example, PyMC, where they were like, we recommend you read the Stan documentation because it has so many techniques on Bayesian modeling, even though then they recommend that you use PyMC, which is a nice probabilistic programming languages. Okay, so here's our example. We're just going to fit a Bayesian linear regression with some prior on our coefficients and our standard deviation. And we're going to estimate the posterior distribution of the parameters, right? A bit of an abstract example, but this is where we're going to start. What I'll say is that really what Stan does is it takes your Stan file and then it transpiles it. So meaning it translates it into C++ and then it compiles it so that it can be executed efficiently, right? So Stan retains some C++ features, but it's much easier to use than C++. So the way we write a Stan file is we'll have these different blocks. One of them is going to be the data, the parameters, and then the model, right? And so with that, we're going to do a coding demo. So this is going to be an exercise that we're all going to do together, right? So hopefully, everything is installed, right? And now I should be able to load the packages. Okay, so I have some utility functions, but this is the code that I care about. So here what I've specified is the data, right, for my linear regression. So we're just going to run this block, right, and also some initial function. So Stan has some default initializers for the Markov chain. My recommendation is to initialize your Markov chains from your prior distribution. For now. Right? If people have like, oh, but I'm going to use a quick approximation, I'm going to do a Laplace approximation or variational inference approximation, sure, you can do that. I recommend starting from your prior distribution. And now, what we're going to do is we're going to construct our Stan file. So on the left side, you can click on the folder icon. We're going to create a new folder. We're going to call it model. Right? And inside of model, we're going to create a new file. And we're going to call it linear.stan. So it could be anything that you want, but just so that it's consistent with the script. Right? And there you go. Okay. So the Colab editor doesn't know the Stan language, so we're not going to have any helpers, but that's fine. We'll do without it. So the first thing I'm going to do is I'm going to specify a data block. And inside the data block, I'm going to have my first variable, which is n, the number of observations, right? And then I'm going to have an initial variable x, which is my covariate, and a response variable y, which is my response, right? And then I'm going to specify the parameters block. So what are the parameters? So we have a real coefficient, beta, and then we have a real standard deviation, sigma. And so one thing that I can do is I can tell Stan, by the way, you know, this is not just a real, it's a real that's lower bounded by 0. Is this big enough? People at the back, can you see? Nice. All right. And finally, I'm going to write what's called a model block. So first I need to specify the prior distributions. Someone looking at the slides, could you tell me what the prior is for beta? Normal to 1, okay. So I can write it as a statement like this. So I should be clear that, by the way, this is not a sampling statement. This is just specifying, you know, I'm going to increase my log joint density by a normal, by beta normal centered at 2 with standard deviation 1. What's the prior on sigma?
Normal plus 1.
Right, so normal 0, 1? 1, 1. And it says in the slide normal plus, so what that means is it's a truncated normal, right? So we're only limiting ourselves to the positive values, so we don't need to do that explicitly because we've indicated, we've told Stan, hey, sigma is lower bounded by 0, right? And now all that remains to do is specify the likelihood, right? So my observation y is going to follow a normal distribution centered at beta times x with standard deviation sigma, right? I will say that the one thing I do like with Stan, and by the way, I should be clear, I like other probabilistic programming languages, and I use other probabilistic programming languages, and I'll talk a little bit about that in the discussion. Where do I think Stan fits in the toolkit? But one thing I do like about Stan is that, to me, this is extremely readable. Like, whenever I'm asked to review papers, if they use a Stan code, I actually check their code. I can actually, like, check, this is what their model does, this is how it's written, and then, you know, maybe I can ask questions and so forth. I do find it more difficult to, with other languages. Now, part of it is my bias. I happen to be extremely familiar with Stan, but I do think that it makes the model extremely transparent. Right. So now just moving, so I'm going to leave this to the side so that hopefully it's still readable. And now I have the transpile step, right? So hopefully it finds, all right, this is linear.stan, and what it's going to do now is it's going to translate it to C++ and then compile it. And this is going to take, this might take a little bit of time the first time you do it, because I think it's building some of the binaries for Stan. All right, so it took a while. Once we start fitting more interesting models, that compilation optimizes a lot of code and it pays off. For a simple model like that, yeah, okay, why did I have to wait so long? And then I have this fit function where I can specify a number of things. So first of all, I need to pass in the data. I can pass in an init, so that's how do I initialize my Markov chain. So here I've just chosen to draw from the priors. I have a keyword that says, hey, I want to save the warm-up samples, right? So we're not going to use them for our Monte Carlo estimators, but we're actually going to examine them for pedagogical reasons. I can specify that I want to run 4 Markov chains in parallel. So we're not going to run a single chain. We'll run multiple chains. I think the CPU on Colab only has 2 cores. So it'll parallelize 2 Markov chains instead of 4. And then I specify the number of warm-up samples and the number of sampling iterations. And here it's set to 1,000 and 1,000. The reason why that is these are the defaults in Stan, right? So we're going to question whether these defaults are appropriate for this problem, but at least we're going to start here, right? And so now I can run the code. And it's telling me num warmup is deprecated. Please use iter warmup and iter sampling. Okay, my bad. End chains, all right, let's get rid of end chains. That makes sense. Sorry about that. Attends. Wait, but we tested this yesterday. This worked fine. Got it. Thank you very much. So my apologies for that. I wonder if there was, between yesterday and today, a new release. But anyways, let me write down on the board the corrections that we're making. That way, as I keep scrolling down, people will be able to keep track of that, okay? So sorry about that. And if you have questions, the TAs can also help. Thanks for the people who stepped in. This is always the adventure when you do live coding. But I think it's instructive, actually. So okay. So just looking at the output, so here it just keeps track of the runs of the chains, the run times. So you know, if you're running Markov chains that take a while, this is useful, right? It's running multiple chains. And now what I can do is I can look at summaries. Right, and Stan is going to output a few summaries. So one of them is it's going to compute this log join density. We're not going to worry about it. I think it's not very useful, but some people like it. But the thing that I want to focus on is I have my parameters beta and sigma, and now I have estimators for various quantities of the posterior distribution, including the mean, the median, the standard deviation, MAD, that's like the equivalent of the standard deviation for the median, the 5th posterior quantile, the 95th posterior quantile. And then I have some other quantities here, which are called R hat, ESS bulk, and ESS tail. So ESS is the effective sample size, right? So I can see that the effective sample size for my quantities is going to be around 3,000, right? So we ran 4 chains with 4,000, with 1,000 sampling iterations each, right? So here we do have some autocorrelation, which is why the effective sample size is 3,000 rather than 4,000, right? This ESS tail, that's when you're trying to estimate extreme quantiles, it can be helpful. We'll define that in a second. And then we have this R hat statistic, that's a convergence diagnostic. When R hat is close to 1, right? So usually you want it to be smaller than 1.05, 1.01. That's an indication that the Markov chains have converged, right? And we're going to explain what all of this means in a second. But what I propose is that we take our coffee break now, right? And then we'll come back and we'll try and understand all the quantities in here. Great. So we had this first example in Stan, and we had these summaries. And now the question that I want to ask is, should we trust them? Do we trust these estimates? How do we know that it's accurate, right? So fine, it returns a number. But remember, Markov chain Monte Carlo, it's a bit of a sophisticated procedure. We shouldn't take it at face value. So let's talk a little bit about how we can, make sure, or at least have some confidence that these estimates are reliable. And one of the first thing is, we need to diagnose approximate convergence, right? So remember, we start from some distribution, P0. That's not our target distribution. We need to make sure that somehow we've gotten to this distribution. And the question is, are the chains still biased by their initialization? And the idea, and so this kind of came up in the questions, is that we're going to start multiple chains from very different locations. We're going to run them using different random seeds. But remember that at the end, the quantities that we're trying to estimate is an expectation value, right? That's not a random quantity. It shouldn't depend on the initialization. It shouldn't depend on the seed. So the idea is very simple. Run your MCMC process with different initialization and different seed, and make sure that you get the same result, right, back and forth. And so there are multiple ways to do this. We're going to be looking at trace plots, density plots, and this R hat statistic. And what R hat does is it looks at the standard deviation across all chains. So it's going to look at the mean generated by each chain. And it's going to ask, is the standard deviation between those means small compared to the standard deviation within each chain? Right? So we'll refine that statement a little bit. But the idea is that if the standard deviation across all chains is small, right? So you take the samples across all the chains, you compare it to the samples within a single chains, right? You should get that those two quantities are roughly equal. And so my R hat statistic should be close to 1. If the chains are in disagreement, it should be much greater than 1. So let's take a look. So first of all, if I look at the R hat statistics for beta and sigma, I see that it's very, very close to 1. Right? So that's giving me some confidence that the chains are all in good agreement. We're going to look at something called the trace plots. Okay, so what do we have here? We have 4 chains, and the gray zone is the warm-up phase. These are the samples that I've discarded, right? And then the chains kind of start at different locations, but actually they very, very quickly converge to the same region, right? And in fact, there's no way to distinguish between the different chains, right? They're kind of like just oscillating in the same zone. By the way, based on this plot, do you think that our warm-up phase was too long or too short? Yeah, way too long, right? I mean, clearly, you converge so quickly that you probably need way less than 1,000 iterations to warm up. And then, this fuzzy shape, so the technical term is fuzzy caterpillar shape, right, indicates that there's actually very little autocorrelation between your samples, right? Your Markov chain is kind of jumping up and down. So this is the sign, of a very healthy Markov chain. I can also look at density plots, right? So I'll look at, various, one-dimensional quantities such as beta and sigma, and you can see that the chains are not in perfect agreement, right? But they're in very, very close agreement. And then, of course, the last quantity that I would examine is the effective sample size. So here it's around 3,000. This is actually very large. I think that, okay, the effective sample size that you need is really problem dependent, right? My guess is you could run a much shorter sampling phase and still get very good estimates of the posterior mean and quantiles of beta and sigma. All right, with that said, so those are our diagnostics. Those are ways to, check the inference, right? So what did we do? We made sure we converged, right, as an indirect way to control the bias. And then we make sure that our effective sample size was large as a way to control the variance, right? And with that, we have some confidence that our Monte Carlo estimator are fairly precise. Yes?
Why is the sigma
So if you look at the posterior distribution of sigma, it's not perfectly symmetric, right? That's your comment? Yeah, I mean, that's just the posterior, right? There's no reason to expect a symmetric posterior or a Gaussian posterior or anything, right? And in fact, if you think about it, we might actually come back to that in a second, right? But the other thing I could have plotted is the prior distribution. Remember, our prior for sigma was a normal centered at 0 with a tail that I think the standard deviation was 1 or something like that. And you can clearly see that based on the data, we've moved away towards the right. Yeah.
If I have that some of the parameters show some convergence, but some others don't, does it make the whole chain non-trustworthy, or I guess it's saying that because are not identifiable?
Right, right. So that's a very good question followed by a very good comment. The question is, if I have, if I observe convergence along some of the parameters but not along other parameters, does that mean the Markov chain is not trustworthy? And really, it depends on, people have different opinions. I tend to be pragmatic. If it converges for the quantities that you care about, to me, that's good enough, right? And the one example is, if you're fitting a Bayesian neural network, for instance, you're unlikely to get the Markov chains to converge with respect to the weights because there are non-identifiability issues. But on the other hand, you can get them to converge with respect to the predictions. And arguably, the quantities that you do care about is the prediction or some decision that you do down the line, right? But those are, this is a question to be answered on a case-by-case basis. Okay, so that's all fine. So we trust our inference. Right. So let me go into this. So the question is, how do I understand what this standard deviation across all chains means? So I was going to skip the next section in the interest of time, but your question convinced me that maybe we should talk a little bit more about R hat, and in the process, we'll hopefully answer your question. Okay? So, so suppose I have theta and m. So now I'm going to denote my sample both using iteration and I'm thinking in the interest of time. All right, let me do this quickly and then follow up with me on lunch. Right, so I have theta and m, the nth sample from m chain. I have some quantity of interest f that maps theta to r. Right, so one way to write R hat is as follows: square root of n minus 1 over n plus b hat over w hat, where b hat is the sample variance of the mean of each chain. So each Markov chain generates one Monte Carlo estimator, is the way of thinking about it. And I'm looking at the variance, and then in the denominator, I have the average within chain variance. So the way that works is for each chain, you look at the sample variance, and then you average it, right? It turns out, if you're familiar a little bit with ANOVA statistics and laws of total variance, you can map this back to the standard deviation across all chains. If not, I'm happy to show you on the board offline. It's a 5-minute discussion that we can have. But the point is, one way in which I like to think about R hat is if you're saying I want R hat to be close to 1 or below some threshold, really what you're saying is I want my b hat, right? So the variance between the different Monte Carlo estimator to be below some threshold that depends on my estimate of the posterior variance, right? So what we're saying is that the variance of the Monte Carlo estimator should be small, but because variance is not a scale-free unit, we kind of scale it by the posterior variance, right? And that should make sense, right? If you have an object where the posterior variance is extremely large, right? The amount of work you need to do to get a Monte Carlo estimator with a low variance is going to be much larger. But actually, a lot of time it doesn't matter. And the reason why that is, the reason why I think we should think about scale-free units is because remember that we're trying to quantify uncertainty, And there are two sources of uncertainty in my inference. One is the posterior variance, right? So that's the uncertainty I get from having, limited data to really, explain my model. And then there is the uncertainty due to my Monte Carlo estimator. And so if you put a lot of work to reduce the Monte Carlo estimator, you might get that component of the uncertainty to be very small, but you still have the uncertainty that's due to the posterior variance. And so at some point, it's no longer that useful to further decrease the variance of the Monte Carlo estimator. That's why we like to think of the variance of the Monte Carlo estimator relative to the posterior variance. Now, there are some examples where actually, you don't care about the posterior variance or the variance of your quantity, and here it makes sense to put more work to reduce the variance of the Monte Carlo estimator.
I'm not sure if I understand the WF because to me it says that within the chain we want to have like large coverage of space, right? But before you already mentioned that this is not exactly what we're trying to aim for.
Alors, so what we want is maybe not necessarily large, but accurate coverage, right? We want the variance of our samples to correspond to our posterior variance. Okay, but the point is, really what we're trying to do is to make sure that the variance of our Monte Carlo estimator is small. I'm going to keep going if that's okay. And I'll leave it at that. There's more to be said about this. We'll take this offline, but in the interest of time, we're gonna move forward. Although I'll point you to two references. One is the paper by Veshtari and colleague, and the other one is a recent paper that I have that digs a little bit deeper into that subject. Okay. So just to summarize, ideally, our hat tells us if the warm-up phase is long enough. The effective sample size, or if you don't want something scale 3, the Monte Carlo standard error tells you if your sampling phase is long enough. As a rule of thumb, I would aim for an effective sample size that's at least 100. But it's going to be very problem specific. You can also look at DESS in detail if you're trying to estimate extreme quantiles. So you want a good characterization of posterior intervals. For example, when you want to try to learn, how likely are some rare events. And then you can also look at the median as opposed to the expectation value and this median absolute deviation. The reason I bring this up is because they're part of the summary that's outputted by Stan. All right, so do you remember the Bayesian workflow from day one? Right, so it kind of says that. So this is the simplified picture. I think Andrew showed you the super complicated graph we have in our paper from 2020. But this is Box's loop. It's the simplified version. And what it says is you build the model, you do your inference, right? And then you do the criticism. And right now, we've criticized the inference. So we've done diagnostics for the inference, but we haven't checked that the model is good or not, right? I mean, who thinks that the model is good? Do people not like my Bayesian linear regression model? Now would be a good time to voice some concerns. Who thinks it's a bad model? Well, we have no idea, right? We didn't check it, right? So let's do that now. And so what we're going to do is we're going to do these so-called posterior predictive checks. So this has come up in the previous days. But the idea is, now that I've fitted my model, I'm going to simulate from the fitted model, right? And so, I've not just learned a parameter value, I've learned a distribution of parameter values, and so that in turn induces a distribution of simulations. And in particular, we're going to construct these so-called posterior predictive distributions, which is going to be P of y pred conditional on the training data, basically. Y, which is just going to be this integral. And we like integrals. We're good at doing integrals because we have Monte Carlo methods, right? Just as a thought exercise, I'll invite people to contrast the quantity we're computing here with this quantity, which has been drastically emphasized over the last days. And we'll talk about it during the discussion section. But keep that a little bit in the back of your mind. And so for now, we're going to go back to our code, and we're going to add a little bit to our stand code so that we can do this simulation, right, of our data. So let's go back to the Colab and code together. I'm actually going to can't edit read-only, okay. We're going to introduce a new quantity, a new block called generated quantities, right? And all I'm going to do is I'm going to construct a vector that I'm going to call ypred. And ypred is going to come from a normal. RNG means random number generator, right? It's going to be centered at beta times x with standard deviation sigma, right? So all I'm doing is I'm simulating from my model, right? That's fine. No, ignore that. It's Google Colab being a bit more verbose. Okay, yeah, so does this make sense, right? All I'm doing is now I'm saying, for each value of beta and sigma that you generate, also generate a set of, generate a new data set, right? And so now I go back to, I'm going to go back all the way, and I'm going to recompile my model. Okay, so now Stan is giving me an error message. It's saying you shouldn't use a vector, you should use an array here. Fine. We'll use an array.
So the error seems to be very helpful.
Oh yeah, the error messages are great, actually. Yeah, it tells you this is the line where it's failing, and you should, hopefully this works. Seems to work. Okay, so now it's doing the transpiling. There's a difference between arrays and vectors. Anyone who does C++ know the difference? Right, so arrays are easier to, it's easier to extract one element from an array. So just in terms of pointers, whereas vectors are more suited for linear algebra. Just a basic intuition. Okay, so now I fit the model. I look at the summaries, and now what you'll notice is that in addition to, my beta and my sigma, I now have a bunch of other quantities which are going to be ypred indexed by 1, 2, 3, all the way up to 10, right? And so what that means is that for each of my 10 data points, I've generated a prediction, and because I'm being fully Bayesian, for each of these predictions, I actually also have a posterior distribution, right, that we're estimating. So now we can go again through the same exercise. You should inspect R hat effective sample size. Can someone check for me that the R hat is close to 1 for all our predictions, and also that the effective sample size is reasonably large? But the point is that I'm going to scroll down, and so now what I'm going to do is I'm going to take these predictions and I'm going to plot them and compare them to the true data. Right? Okay. So this is what this looks like. So the circles here represent the true data. And then the median, the dark line here, is going to be the posterior median of my predicted data. and then I have a 50% posterior confidence interval and 95% posterior interval, right? And so if I look at this plot that compares the simulations from my model to the true data, I mean, it looks like I have a very good model, right? No? Who said no? Yeah, what's wrong with that model?
You don't have a bias term in the linear regression.
Yes, we don't have a bias term, or another way to put it is we're clearly missing an intercept, right? So, and so the point is that it's not that people fit linear regressions without intercepts, but the point is that you can do the diagnostics, you can fit the model, the inference can look fine. In fact, the inference is fine, right? We are correctly estimating the posterior distribution, but nonetheless, your model can do a poor job describing the data. So that's why we need, you know, after we've checked the inference, we need to also check the model and the output of the model, right? So as an exercise, right, I'm going to ask you to, you know, just add an intercept to the model, run the model, check the inference, and then also adjust the predictions and check the predictions. And we're going to do that for 10 minutes, okay? And then I'll go through the solution, right? I don't think it's... Well, we'll do 10 minutes, and then if people have questions about this, feel free to raise your hands. The TAs and I are at your disposal. All right, just by a show of hand, how are people doing? Do we need the full 10 minutes, another 5 minutes, or are people able to complete the exercise, ready to move on? Okay, I see some thumbs up. If people are ready to move on, yeah, okay. So I think I see enough non-thumbs up that I want to give people time to play a little bit with this. But let's say we'll do 2 minutes, and then I'll code up the solution, and we can keep moving. All right, so this is my attempt at the solution. So I've just introduced an intercept term, beta 0, right? And then in the model, right, now instead of having a normal that's centered at beta times x, I have it centered at beta 0 plus beta times x, right? And then I also need to remember to adjust my posterior predictive checks so that it's also centered at beta 0. The question is, what is the prior on beta 0? The answer is this is a toy example, right? This is not real data. We don't really have a good way to reason about it. There's no universal prior on beta 0 that you would put for an arbitrary data set. So for now, we're just gonna say, you know, it doesn't really matter, right? But it's true that in practice, you would have to worry about a prior. By the way, you don't have to specify a prior, so, which is equivalent to specifying a flat prior. Okay. So let me just... Oh, just because it's a toy example. In practice, you need to set the prior. Yeah. But here, you know, the data is like not very interpretable. So it's not exactly, you know, I could say, hey, this is the heights given the parent's heights or something like that, and then we can think a bit harder about the prior, you know, but for now, we'll just sidestep that question. Yeah. All right, so by the way, so, you know, this is the kind of fit that you can get. And so one thing that I would examine is not just that my fit is describing the data well. I also want to make sure that the uncertainty is well calibrated, right? So the posterior variance shouldn't be too large or too small. And so maybe one idea is, you know, if I look at the 50% posterior interval, I'd want roughly half of my data to fit within that interval and half of my data to fit outside of it, right? So that's something you can check. All right, we're going to move on. We're definitely not quite in the times to cover all of the material, at least not if we did the exercises. So maybe we'll stick a little bit to that demo format. And now I want to talk about a more involved example, still a somewhat accessible one, which is a disease transmission model. And so this is based on a paper we had with some colleagues in epidemiology during 2020, very early during the pandemic, when we had the first infectious cases, right? So at the time, the data you had was in China, specifically in Hubei, and then in 6 regions of Europe, right? This is when the pandemic was starting to spread. And the question is, we have very limited data. We have very biased data, actually, in some sense. Can we get estimates of the mortality rate? Can we try and model, you know, what would the effects be of a confinement, not confining, and so forth. And so this is the kind of model where now your likelihood is going to be more complicated than a normal likelihood, where you have an epidemiological model that underlies the disease dynamic, right? So that's going to be something based on a system of differential equations. And then we also need a measurement model, right? So what do we include in the measurement model? Well, for example, we had test results. And so for each country, for each region, you get, you know, what are the number of infected patients. But you might remember that at the beginning of the pandemic, tests were not widely available. Tests were very limited. So who were the people who got tested? The people with strong symptoms, right? And so that means that if now I'm calculating the mortality rate based on, you know, amongst the people who test, how many of them passed away, am I going to overestimate or underestimate the mortality rate? Overestimate it, right? Because I'm only looking at people with strong symptoms. So you need a model that kind of accounts for that. Hospital deaths, that's the opposite. A lot of people who are going to die are not dead yet, right? So now you have a bias in the other direction. For the priors, we have a lot of parameters that are interpretable, that have an epidemiological meaning, so we can draw some expert knowledge, maybe some knowledge that we have from other epidemics and diseases. And then we had one very cool prior. We had this thing called the asymptomatic rate, where, you know, in order to actually say something about a population, we need to say, you know, what is the proportion of individuals that actually develop symptoms? And we don't know that because we're not testing everybody. But there were some instances where a whole population had been tested. So there was this cruise boat in near Japan called the Diamond Princess. They had one of the first cases of COVID. Quarantine, everybody gets tested, right? And so just from that small population, we had some estimates of these are the number of people, you know, with symptoms, who are sick with symptoms, who are sick without symptoms. Of course, it's a very small population. So we want to construct a prior that accounts for the uncertainty in that population, right? And these are the kind of more sophisticated models with a lot of different moving parts and moving components that you start being able to build inside of STAN. We're going to do a simplified version of this, where it's an influenza outbreak in a British boarding school, where we just have, you know, the daily number of students in bed, right? And you can imagine how, you know, if one person gets sick in a boarding school, it spreads out very quickly. If one person is sick at a summer school on probabilistic AI, chances are next week, no, don't worry about it. I mean, hopefully not, right? Hopefully not, but okay. And so the model, and this was widely used, kind of looks like this. It's a compartment model. And so the idea is we're going to divide the populations into individuals that are susceptible, infected, and recovered. And then at a certain rate, you're going to move from one compartment to the other, right? And so in particular, we have this beta, which is the transmission rate. So that's a parameter that dictates, you know, if, you know, I have a certain number of people who are, you know, if I have a certain number of people who are sick, you know, so how quickly is the disease going to spread from the susceptible to the infected compartment? And you can see here that, you know, the rate at which the number of infected people increases depends on the transmission rate. It depends on the number of people who are susceptible to an infection. And it also depends on the number of people who are infected, right? Like the more people are infected, the more you are likely to come in contact with them. And then it's divided by n. Because if my total population is very large, then the odds that I come in contact with an infected people become smaller, right? And of course, the rate at which people recover, well, the more infected people you have, the more people will recover. That's what you want to expect. And so the idea is that we're going to try and fit this model and then estimate some quantities, right? So what are quantities we might want to expect? When is the disease going to peak? If I'm sick, how many days will it take me to recover, right? I got sick on Tuesday. I have a birthday party this weekend. Am I going to be able to attend, or do I have to cancel? I mean, maybe not a birthday party. I have a flight to the summer school on Probabilistic AI, right? Those are all questions that we can try to answer. Okay, so now the question is, which measurement model should we use? So I'm going to give you two candidates, and we're going to have a vote. One candidate would be a Poisson likelihood. So this is a count data. And the idea is that we're going to take measurements that are imperfect, right? So we don't actually monitor exactly who's infected or not. We monitor who's in bed. And if someone is in bed, we're going to be like, oh, okay, they're probably sick. They have symptoms. So the Poisson distribution, the expectation value is going to be the number of infected individuals. And then the variance is also going to be the number of infected individuals, right? So the idea is that the higher the count, the higher the variance in my distribution. We're actually going to skip the coding this in Stan, right? I'll just do it just in the interest of time, right? But what you can do in Stan is you can actually write down an ODE, a differential equation that you then solve inside of the model block. And then the solution to that differential equation is going to return the number of susceptible, infected, and recovered individual over time. And in particular, the second compartment, which is the number of infected people, is going to be what's going to parameterize my Poisson distribution. Right? So that's how I'm going to define my likelihood. I'm now embedding a scientific model inside of my statistical model. The other thing that we could use is something called a negative binomial distribution, which is a generalization of the Poisson, where again, the expected number of cases is the number of infected individuals, but this time the variance is controlled by a parameter, and in particular, we're allowing for over-dispersion. We're allowing for the variance to be larger. So there's more flexibility in this model. Okay, so we have some priors that we can use, and now we have an interpretable model. But essentially, I got those priors from my colleagues in epidemiology based on their expertise on, you know, what kind of infection rates we can expect from similar influenza epidemics. And, you know, the way they reason about this is they say, you know, we're going to put a normal distribution on this infection rate, and we're going to restrict it to be positive. Well, we know it has to be positive, right? But also, we're going to make sure that with very high probability, the infection rate is below 4, right? And then they find the normal distribution that matches this probability. That's kind of their reasoning. I'm putting a reference here where we work out in greater detail how we do this. And now just going in the code, so what I've done is in the GitHub repository, you actually have all the Stan code. Usually with more time, I would make people write this Stan model. But here we're just going to take it for granted. I'll just show a little bit what's inside of it. So I have a new block called the functions block where I specified the differential equations that I want to solve, right? So you can see that this looks like the ODE that I specified. Then I have my data, the parameters I'm trying to infer. I'm solving my ODE. This is an ODE solver, Rongakata 4th and 5th order. And then again, I have my model and my prior. And then in generated quantities, I'm going to generate some predictions and some other quantities of interest. We'll talk about this in a second, right? Show of hand, who thinks we should do a Poisson likelihood, and who thinks we should do a negative binomial likelihood? All right, Team Poisson, raise your hand. That's it? 1, 2, 3. Team negative likelihood. Negative binomial. Okay. More people. So more people are in favor of the negative binomial. So we're going to fit both models and we'll compare them. Right? Okay. So, so this is the data that we have. So you see it kind of has this wave curve, right, that you would expect. Generate the data. Again, I'm just going to draw my initial distributions from the sampling iteration. One thing you could play with is how many chains you run. So I'll probably need to adjust this. And the length of the Markov chains, right? So that's something I encourage you to experiment with in your own time. How can you make the Markov chain as short as possible while still getting all the scientific results that you care about? So now num samples and num warm up. Oops, okay. So what it's doing is it's running, and then this model takes a little bit more time than the linear regression. That's because now at each iteration of MCMC we need to solve a differential equation inside. But okay, within a few seconds we get the wanted results. And so now once again I'm going to do my checks. And there are a few quantities that I'm going to be interested in. So one is going to be gamma, which is the recovery time. The other one is going to be beta, which is the infection time. I'll look at phi, which is the overdispersion in my likelihood, and I'm going to look at this R0 quantity. And so R0 tells me if an individual is infected, how many other individuals would it infect? So I remember that during the pandemic, R0 was the quantity that was reported in the newspaper a lot. And the reason why that is that if R0 is below 1, then that means the epidemic is receding, right? Because if each individual infects less than one individual, then the epidemic is going to die down. If they infect more than one individual, the epidemic is going to increase, right?
But can we then actually use R as like a constant value? Shouldn't that be time dependent?
That's true. It should be time dependent, right? Within a short period of time, you treat it as constant. And so what epidemiologists ended up doing is they would regularly report R0 this month, right? Or this week. And of course, if suddenly R0 goes from being below 1 to being above 5, then you know you have an epicenter for the disease. So those are the kind of quantities we want to monitor. But also, I should say that we have some uncertainty in our model, right? We have some uncertainty in our data. We have a lot of sources of uncertainty. So actually, we're not just going to look at the expected value of R0. We really want to look at the posterior distribution. And so maybe what I will say is maybe I'll report the 95th posterior quantile kind of as not exactly a worst case scenario, but as a bad case scenario to try and be a little bit conservative, to identify, am I at risk of the epidemic starting again or not, right? But now you can convince yourselves that if you look at things like R hat or the effective sample size, R hat is close to 1, the effective sample size is very large. And now again, I can look at these trace plots. And again, if I use Stan's default for the warm-up phase, it's clearly way too long. Right? And you can also look at the sampling phase. I encourage you to, try different length for the warm-up phase and the sampling phase. And what I did find is that, oftentimes the defaults we have in MCMC software tend to be too conservative. And they're conservative, because statisticians, it's fair enough, right? They'd rather be too conservative than be too optimistic. But then, you get a lot of papers explaining to you that MCMC is so expensive that we can't use it. Well, it depends on how you use MCMC, right? And I think that oftentimes MCMC is cheaper than people suspect. I wrote a paper with Andrew Gelman called For How Many Iterations Should You Run MCMC, where we worked through that example and we show that actually you really, really don't need a lot of iterations to get all the scientific insights that an epidemiologist might want. Okay, those are my predictions. Not too bad, right? It looks like I'm able to capture, you know, the dynamic of the epidemic. What about the uncertainty? Is it well calibrated? What do people think? Is my posterior variance too small, too large?
I would say half is in the roughly half is in the darker area, so you said that's probably what we're aiming for. So
Yeah, that's a good observation. So the comment was that if you look at the dotted points, about half of them fall within the dark region. So that's the 50% posterior interval, and then the other half falls outside. Now, the thing to note is that it's not really heteroskedastic, right? Like there are regions where a lot of points fall outside, and then regions where a lot of points fall inside, right? And that's because, you know, the disease transmission model that we use, the underlying ODE, is a little bit simple. So it doesn't exactly capture the dynamic of the disease. And so the way the model compensates for that is by increasing the posterior variance, right? But that's kind of a way of seeing that, you know, oftentimes, not always, but oftentimes the posterior variance is going to account for some uncertainty in your model when it's not able to perfectly describe your data. All right, so team negative binomial, this is your outcome. Where are my Poisson people? Who's ready for the reckoning? Let's see what happens. Right, same procedure. So again, in the course files, you'll have access to the stand file for the Poisson. I apologize that we don't have the time to have you code it yourself. But there's plenty of documentation and resources online for people to dig into this. And again, if people have questions after the course or follow-up, or even want to work through this during lunchtime, I'm at your disposal. All right, so this runs a little bit. And by the way, I should say, you have these warning message early on, right? These warning messages are telling you, hey, I'm not able to solve the ODE. That's because initially the Markov chains start in regions of the probability space where the parameters have implausible values. And if you plug in those parameter values in the ODE can be very difficult to solve. But eventually, as you start converging, the warning messages start disappearing. And once we're really in the region where the posterior mass concentrates, I'm able to solve the ODE just fine. Okay, so this model runs much faster. Okay, now let's do some predictions. Can't find the following pars. We have to redefine pars, exactly, because we don't have this phi parameter anymore, right? So that's fine, so we'll do that. I'll send an updated notebook. There we go, out with you. But all the other parameters are still here. And so now you'll see that my R0 is, it's not the same, it's much larger, right? So I think that for the negative binomial, right, R0 was, the expectation value was close to 2.6, so we can check that. Here the expectation value is close to 3.5. The quantiles are, the posterior intervals are very small, between 3.4 and 3.6. If I look over there, right, okay, around 3.2, but the interval is much larger, 2.8 to 3.6. So R0 is larger with one likelihood than the other, right? So the model does matter, right? It does change my conclusions a little bit, and especially the uncertainty. All right, but that doesn't really tell us which model is better, right? If I look at R hat and effective sample size, they look fine. for both models, so I'm able to fit both models. And now, drum roll, this is the fit I get with the Poisson distribution. Is this better? What do people think? Who thinks it's better? The Poisson people think it's better. But actually, let's think about this. Why is this better? Or why is this worse? When I say why is this worse, new hands rose. So with the 2 sigma black hat.
I think the meaning looks a little bit better than the other model, but it's concerned that there are things outside of the confidence interval, like there are quite a number of data points outside the confidence interval. So it seems the variance should be bigger if our models would be kind of like.
Yeah, I love that. I think that's spot on, right? So I'll just say your answer again for the posterity, which is that it looks like the mean fit is quite good and even better than in the other case, but the uncertainty is not well calibrated. And in particular, you can see that the number of points that are outside the 50% posterior interval is way larger than 50%. And if I look at these last few points, right, these 3 points are outside the 95% posterior interval. In fact, they're very, very far outside. And so according to our model, these 3 points are completely implausible, right? Which is not something we had with the negative binomial, right? So it's not super clear. So let's try and find a more principled way to compare these models. And this will also allow us to introduce a new Monte Carlo method, which is importance sampling. And so we want to try and characterize whether we get better predictions from the Poisson likelihood or the negative binomial likelihood so that we can, end this internal conflict we have in the classroom. And then the proponents of the better likelihood get to go on the canal tour while the other ones have to stay here, right? Okay. So the idea what we're going to do is instead of doing these posterior predictive checks where we're just seeing does our model describe our training model well, we're actually going to test model predictions on a validation set. So data that has not been seen by the model yet, right? So we'll split the data into a training and a validation set. The posterior is now done conditional on the training set. And then what I would do on the validation set is I would compute a prediction error, right? That's the most vanilla way of doing this. So let's say I want to do predictions at time 12. I look at my prediction at time 12 and I compare it to the actual one, and then I look at the squared error, right? But when I do that, there's no regard for uncertainty quantification. So let's try and do this a little bit better. So let's say I have a Gaussian likelihood, for example. This is not what we have, but we'll look at more general likelihoods in a second, right? If I look at this criterion for prediction, I'm not accounting for my estimate of sigma, right? And so instead what people do is they look at the log predictive density, right? Where they look at the log of p y val given the posterior that I have. So I'm looking at my log likelihood, and it has a nice interpretation in the Gaussian likelihood where now I have this squared error again, scaled by my variance with some penalty for being overconfident, right? Underconfident, actually. So what does this mean? This means that if my prediction is good and my confidence is high, so sigma is small, then this value is really going to be large, right? It's going to explode. I'm going to be rewarded for confidently making a good prediction. On the other hand, if my prediction is very bad, but but I'm extremely confident, then suddenly this quantity becomes very large, and I have a very large negative contribution to my score. Finally, if my prediction is bad, but I'm not too confident, so I have a large sigma, then the contribution of the bad guess is not as large, right? So that's one rule that is going to account both for the accuracy of our prediction and for our uncertainty quantification, right? So you can do that with any likelihood. So for example, with Bernoulli, it also has a nice interpretation, where here, what ends up happening is I'm doing classification 1 or 0, right? If I classify correctly to 1, and I say that the probability of this being 1 is very large, then my score increases a lot. If I classify incorrectly, and I've done that with a lot of confidence, then my penalty is very large, right?
But this obviously prefers over the first likelihoods.
Well, remember that we're kind of like taking into account also the, you are rewarded for confidence. If your predictions are good, you get rewarded for confidence. So your over dispersion might have a larger variance, but if it's, if your predictions are good, then it's better to have a smaller variance because you're more confident, right? So it's not obvious that you get rewarded for over dispersion. Right? That said, it's also not obvious that you get penalized for over dispersion, because if your predictions are not perfect, then it's better to not be overconfident. You hear that, ChatGPT? Right. All right, so the last step is that, we want to do this in Bayesian, in a Bayesian setting, where instead of having a point estimator for each parameter, what I actually have is a distribution for all the parameters, right? So we need to take this a step further. And the way we're going to do that is, instead of just looking at the log likelihood score or the log predictive score, we're going to integrate the log predictive score over all the plausible parameters of theta. And we get this so-called expected log predictive density, right? So this is a way for us to account for uncertainty calibration in our prediction and account for the uncertainty or the spread of values in our inference. Is this perfect? No. Right? There are other criterion that you can use to compare models, right? But this is a criterion which, unlike just looking at the prediction error, takes into account uncertainty and also the fact that we have a full Bayesian posterior as opposed to just a point estimate.
Is this criterion comparable to the fairness of models?
Yes, because for each of the models, I can compute the log of the posterior predictive distribution. So it is, absolutely, and that's one of the strengths of this criterion. Okay, so now I have a problem, which is that I want to split things between a validation set and a test set. A training set and a validation set. And the problem is that when I do that, I use less data to train my model, right? So instead, what people do is this so-called cross-validation scheme, where what we're going to do is, so that we don't have to do the split, we're actually going to ask, if I exclude one data point, right, any data point, how well can my model predict this excluded data point after being trained on all the other data points, right? So this is what this means. I want the log of P of yi, given that I've trained the model on all the y's, excluding the ith observation, right? And this is going to be leave one out cross-validation. And so just as a recap, right, we went from prediction error based on the best prediction, point-wise log predictive score to account for uncertainty, then expected log predictive score to account for the fact we have a posterior distribution. And now I'm telling you we're doing leave one out cross-validation. But the problem with leave one out cross-validation is that if I want to do it exactly, I have to refit my model for each observation that I have. That's super expensive. That's not practical, right? So we're going to try and come up with a more efficient way of doing this, and this is going to come from importance sampling. And the idea with importance sampling, is that I'm trying to compute an expectation value with respect to a measure L, but I don't have samples from L of theta. What I do have is samples from another distribution, Q. And so in our example, you know, let's say we have samples from the posterior distribution, right? So we're willing to fit our model one time, but really what we want is samples from the posterior distribution after excluding the ith data point. So what I can do with importance sampling is I can note that actually this expectation value can be written as another expectation value with respect to Q of theta. Right? All I need to do is I introduce these weights, L of theta over Q of theta, right? And then, in principle, using samples from Q of theta, I can construct a Monte Carlo estimator of the quantity of on the left-hand side, right? And so in particular, what we're going to do is we're going to train our model once to get samples from the posterior distribution, and we'll use that as what's called a proposal distribution to then estimate expectation values with respect to these P of theta given Y with the ith observation excluded for all the observations. Right? So we'll have one proposal distributions that we'll then use for all the target distributions. And so this is going to lead to the importance sampling Monte Carlo estimator. Now in practice, this thing can have a very large variance, so it may not be reliable. Now the nice thing is that when you have a lot of data and you do this leave one out, the posterior distribution tends to be a pretty good estimate of the, let's call it the partial posterior distribution. So this is what's called the importance samplance Monte Carlo estimator. Again, it's just an average, but now each sample is weighted by an importance weight. The practical concern is that this important weight can have a non-finite variance. And so in the interest of time, I'm going to skip a little bit ahead, but what I'll say is I don't have a solution to make the variance of the importance weight finite. What I do have is a diagnostic to check that the importance weight is finite. And so if my diagnostic warns me that the importance weight is not finite, then I'm not going to trust my importance sampling Monte Carlo estimator, and I might do something a little bit more brute force. All right, so we go a little bit into the details, and I apologize, I'm going to go through this quickly, just in the interest of time, because I want us to spend a bit of time on the discussion. So this is just introducing the diagnostic, and then, you know, this is the quantity we need to compute, so we'll have to evaluate the log likelihood inside of Stan and then report that so that we can construct this estimator. And so we're going to use this criterion to compare my disease transmission model with a negative binomial likelihood and with a Poisson likelihood. And crucially, I'm not going to refit the models. Right? I'll use the model fits that I already have to then construct this estimator using leave one out cross-validation, because I'll be using importance sampling, so I don't need to generate new samples. Right? And then we'll get the leave one out prediction score. So before we do that, do people want to switch teams? Who is with Poisson? Who is still Poisson? Team Poisson? Where's your hand? Team Poisson, okay. Who's team negative binomial? All right. So let's see what happens. Alors, it's complaining that some paradoxes were too high. Let's see. Okay. Here's what's happening. So what it's saying is that, okay, so for some of the, so there's one data point there's one partial estimate that wasn't estimated super well, right? But it seems to be correct. For most of our data points, it looks like we're doing a good job estimating those. And in particular, now I'm going to look at the estimated log likelihood. So this is for the Poisson distribution. You see that the score is minus 83.1, right? So that's actually a difficult quantity to interpret on its own, but it has value because it means we can compare it to what we get with a negative binomial. Here, actually, all our estimates are good, and you see that the final estimate is minus 64.1, which is a higher score than with the Poisson likelihood. So the negative binomial likelihood, according to this test at least, gives you a better prediction if we also account for uncertainty calibration, right? And the reason why that is that if I look at the Poisson, you really have some violent outliers, right? Or so some samples which, according to your model, are described as violent outliers. And so then if you remove these points, you will have a very difficult time making accurate predictions about them. Now, that said, I encourage you to think critically about, is this score really that valid? Maybe you're not interested in predicting every point equally. Maybe you only want to predict points in the future. Maybe your goal is to get a good estimate of the peak of the epidemic so that you can manage hospital capacity, right? There are more refined ways of doing these comparisons.
Before you start testing, how do you decide which likelihoods to test? Why did you do a Poisson?
Yep. So in this example, the reason why we did the Poisson likelihood is because we had count data, right? So we knew that we're counting the number of individuals, and so that prescribes a discrete distribution, and the Poisson is the first example of that. Now, epidemiologists in practice will use the negative binomial more because it's more flexible, right? But at least for this example, I was curious. I wanted to see if I use a simpler likelihood, do I actually get better results? And even though my expected log predictive score is worse, I still think this Poisson likelihood is interesting. I think it can have some applications beyond the negative binomial. So here, the way I picked my likelihood is I have some understanding of where my data comes from, right? And I use that to construct the distribution. But yeah, ultimately, there's a deeper question of how do we pick a model? How do we pick a distribution? I think that one of the nice things with the deep learning literature is to kind of say, we're going to pick a model that has maximum flexibility, and so then implicitly training the model is what picks the model, right? But even when you have a deep, a deep learning model, right, you're still using oftentimes a Gaussian likelihood or a Poisson likelihood or a categorical likelihood. And that just depends on the data type that you have. Yeah.
So would you use a normal for the first round?
So you can use a normal, and you could try it actually and see what happens. It's not going to work that well on that example, but if now you had a much larger population than what we have, even though the counts are technically discrete, when you have a large population, the normal ends up doing just fine. And you can show that a normal distribution can be a good approximation to a Poisson distribution with large counts. So there are some limits where a normal distribution is valid. Actually, if I really paid attention to my data, what I should use is a binomial distribution. Because the Poisson allows the count to go to infinity, but I know that the count is capped by my total population. Right? So I could bake more information into this. So, it's a model, it's an approximation.
How do we decide a trade-off between confidence interval and being estimated? Because it seems like you said, with Poisson and the prior are useful because they
Yes. Yeah, so definitely. So I think one of the interesting things with those two likelihoods is that they enforce a trade-off, right? So that's something I wanted to emphasize. Now, if I were actually working with, if this were a real problem that needed urgent solving and I'm working with epidemiologists, actually the next model I would try is, rather than pick one likelihood or the other, is I would refine my disease dynamic model. Because this 3-compartment model fails to capture some of the dynamics of the epidemic, especially towards the end with the tail. What I'm not doing a good job at is calculating the tail. And I think that if I improve the underlying scientific model, then I can actually get a better fit with the negative binomial, which is not going to be underconfident. Yeah.
To inform your model choice so that both scores should converge.
Yeah, I mean, again, it's kind of like at some point, these trade-offs arise because your model is imperfect. If I had a perfect model, then I would just do that and I wouldn't have any trade-offs, right? In practice, we don't have perfect models, we don't have perfect approximations. So what we need to work out is, what are the things we're trying to get out of these approximations, right? And then control the compromises imposed by the models, right? So you can have a model that maybe does a great job estimating the peak of the epidemic, because that's what you care about, but doesn't do a great job estimating the tail of the epidemic. Or maybe you have a model that does a really good job estimating the recovery time, right? And so, I think that ideally we're able to build a model that does a good job everywhere, right? That's kind of an ideal to strive for and to push for, and sometimes we're able to do that, sometimes we have to compromise. Yeah, cool. All right, so I want to just make some concluding remarks. We have about 5 minutes. So just because in the context of this probabilistic AI summer school, we've kind of seen different methods to do the same things. And I want to do a high-level comparisons between Markov chain Monte Carlo and variational inference. So very, very high level, just as a conclusion. And I'll say that I do a lot of work on MCMC, I do a lot of work on VI. I use both methods. And I think we're fortunate to have both methods in the toolkit. Here's the first things that I'll say is that for variational inference, I need to build an approximating model, right? I need to pick what is the variational family that I'm going to use in order to get a good approximation of my posterior and my target distribution. And sometimes there's a straightforward way to do this. So for example, when my likelihood belongs to the exponential family, when my likelihood, involves a system of differential equation or a more sophisticated scientific model that I have to build inside, or maybe, some complicated priors and so forth, it's sometimes less clear how do I pick a variational family to do a good approximation of the posterior distribution, especially if I don't know ahead of time what my posterior is going to look like. On the other hand, what I have found with Markov chain Monte Carlo is that usually I can use a general transition kernel like Hamiltonian Monte Carlo. So observe that between the Bayesian linear regression and the disease transmission model, I have not had to change my MCMC algorithm. And I was able to use the same tool between these two models. And in particular, as we go through various iterations of the models and make them more complex, it's very convenient to be able to revise the model without having to revise the inference algorithm at each iteration. That said, there are black box variational inference algorithms that use variational families that can be very rich. So for example, one based on normalizing flows, and I think that in the future, these will kind of bridge the gap between this generality of MCMC and what we're seeing with VI currently. Variation inference, oftentimes you'll find when you do these comparisons, and I saw even yesterday some posters who made these comparisons, the error goes down very quickly initially. And so when you have big models, a lot of data, strong computational constraints, right? under a finite computational budget, you might find that you get a better error overall, or better performance, however you want to measure that, with variational inference. Whereas Markov chain Monte Carlo can take more time to get going. Now it depends on which MCMC algorithm you use and how well you tune it. On the other hand, a variational inference at some point is going to be limited by the variational family that you have, which means that as you start throwing more computation at it, you're not going to get a better results. And so one way to see this is that it's asymptotically biased, whereas MCMC has this nice asymptotically unbiased property, which means that if you throw enough computation at it, eventually you're going to get results that are arbitrarily good. Arbitrarily good. The other thing that I'll say is that when I run MCMC, I have a lot of diagnostics at my disposal to check the quality of the inference. Did the Markov chains converge? What is the effective sample size? Are the different Markov chains in agreement with one another? And the remark that I'll say is, in 2 days of doing work with variational inference, the only times we've checked the inference is when we had a golden benchmark for what the true posterior was, either as assessed through analytical calculations or by using an expensive run of MCMC. So there's a real, I think, limitation with variational inference that you get your estimates of the posteriors. Okay. Is it a good estimate of the posterior? Is it a bad estimate of the posterior? It depends on a case-by-case basis. Is the mean field assumption, where I'm assuming factorize, causing me to draw, bad estimates of the quantities, or maybe I still get good estimates? It's not super clear. And there's a nice branch of research where people are trying to come up with diagnostics that have the same quality and theoretical underpinning as MCMC for variational inference, but it's not deployed universally as far as I can tell. That said, I'll point you to the work of Aki Vatari, Jonathan Huggins, Tamara Broderick. They're doing some great work on trying to diagnose the quality of variational inference. That said, in either case, you can check the trained model. That we've done with MCMC, and we've done it with variational inference as well, right? Where we look at, does my variational autoencoder perform a task of classification image compression well, right? Am I doing a good job describing my data, right? We did that with MCMC as well. And one of the lessons from our first example is you can have good inference and bad model performance, right? The reason why I like having both diagnostics for the inference and for training the model is that if once I check the trained model, things look bad, I find it useful to be able to distinguish between there's a problem with my model versus there's a problem with my inference. Again, example that came up yesterday, the variational autoencoder. Suppose your VAE doesn't do well. Well, is it a problem with your model, your decoder, or is it a problem with your inference, your encoder, right? So I think there are real benefits in, and this came up in, decoupling the modeling and the inference, and I think that this decoupling also needs to happen in our diagnostics. I'll leave you with this plot about, it's a sketch. I think there's some interesting theoretical work about formalizing this sketch, but this idea that, if my computation time is limited, and the reason why that is maybe not because I have, not super powerful computers, but because I have massive data or massively large models, then VI might get me a better solution faster. You might also want to think about, is this error here tolerable for my scientific application? Or am I working on a critical application? So when I work in epidemiology or in pharmacology, where we're doing clinical trials, we want to get very accurate results, right? If I'm doing image classification, image compression, and so forth, I want to get accurate results, but usually I have some leeway for failures, right? So it's good to think about what is the error that we can tolerate, and can we also characterize the error that we get? Or are we in a regime where either we have more compute or less error tolerance? Right. I have some more remarks about Stan, but I think I'll leave it there. I saw yesterday someone advertising a summer school. I'll advertise a conference that we have on Bayesian modeling and StanCon that's coming up this September. If you're interested in the kind of things you saw this morning, right, this will be that on steroids. Don't do steroids. But you might find that interesting. And so with that, we are at our lunch break. I went a little bit over time. I'm happy to stick around for discussion.